Hi, I'm Ryan, and I'm going to show you how to build an app like this example. First, we'll fit a scikit-learn model to predict penguin species, either chinstrap, Gentoo, or Adelie, based on the penguin's bill measurements. Then we'll deploy that model in this web app. Here's what it does. Click on Predict here, then the Try It Out button. Input the penguin's measurements, bill length, and depth, and click the Execute button. Behind the scenes, our scikit-learn model predicts the penguin species, and we get a response here, Gentoo. Change the bill length and depth. Click Execute again. We get a new response, Adelie. Our app validates these inputs too. Watch what happens if we use nonsense inputs, like a negative bill length or an impossibly large bill depth. The app responds, "This input is unprocessable." And here are some helpful error messages to explain what went wrong. So this app has a UI, a user interface. It's also an API, an application programming interface. It's a web service for other applications to request predictions. You can write code to post penguin measurements and get a species in response. You can make requests in Python like this, or other languages like JavaScript. This is a scikit-learn model deployed as an API. It's what you do after model.fit, and we'll do it all in Jupyter. You can follow along step by step. Go to the GitHub repo, and in the README, click the binder link. Within a few minutes, you'll have a notebook running in the cloud with all requirements installed automatically. Select the notebook subdirectory, and then open the notebook file. Part 0 is to fit a model on the Palmer Penguins dataset. First, we'll load and explore the data. We see these penguin species can be classified by their bill measurements. So, we'll fit a logistic regression model. And yes, it classifies these penguins nearly perfectly. So let's start building the app for this model. Web apps aren't usually served from notebooks, especially temporary cloud notebooks like Binder, but it can be useful for rapid prototyping, so this helper function will make it possible. Now, part 1 is like Hello World. Before we make real predictions, we'll make random guesses. We can write a function like this. Run it, and you'll get random penguin species. We can turn this function into a fast API app running in our notebook by adding just a few more lines of code. This line imports fast API, and this line creates a fast API app instance. This decorator tells fast API to call the function below whenever the app receives a request to the root path using the HTTP GET method. This line enables running fast API from a cloud notebook. And this line imports Uvicorn, the recommended web server for FastAPI. And finally, this line uses Uvicorn to run the app. So let's run this code cell. You'll see a public URL that ends in ngrok.io. Click the link to open it in a new tab. You'll see a random penguin species here. Refresh the tab to get another random penguin. Every time I refreshed, it shows up in the web logs here. The app is up on the public internet for anyone to access, but only while this cell in this notebook is running. So I'll stop this cell from running now. You see the application shutdown is complete. And now if I refresh this tab, I get a not found error. So I'll close this tab. Next, we'll add an app title here. We'll change this parameter, docs URL, and we'll change the path from the root to /random for this random penguin function. So run this cell and click this new public URL. We see automatically generated documentation here. And it's interactive too. If we click on random, then the try it out button, then the execute button, and scroll down to the server response, we see a response body with a penguin species, Adelie, and code with 200, which is a successful status code. Hit execute again, and we get another random penguin species. Or we can change the end of this URL to random. We can use the API directly, like before. I'll go back to my notebook and stop this cell from running. Okay, now that we've achieved hello world, let's move on to part 2, adding our model to make real predictions. So to make a prediction, we need data. We need penguin measurements, which we will receive as JSON. It looks a lot like a Python dictionary, like this example here. These measurements would be characteristic of the Gen 2 species, and this is a particular penguin, so we give him a name, Gary Gen 2. Now, how would we go from JSON or a Python dictionary format like this to something that our model can use? Well, we would need either a NumPy array or a pandas data frame with 2 columns for our 2 features and 1 row for our 1 observation, our single penguin that we want to predict. Well, we can make a data frame from a list of dicks like this. And here we have a pandas data frame with the 2 columns for our 2 features and the 1 row for our 1 penguin, Gary Gen 2. And we can use this data frame with our classifier's predict method, and we get the correct result. Gary Gen 2 is in fact predicted to be a Gen 2 penguin. Notice also that the predict method from scikit-learn returns a NumPy array with all of our predictions. But really, we're just making a single prediction. So we want the 0th item from this array. And if we do that here, and we put it all together, we could write a function like this, predict species. When we use Gary Gen 2, this dictionary as the argument for a predict species function, we again get the correct result, Gen 2. Here's another example with measurements characteristic of an Adelie penguin. So we will name this particular penguin Amy Adelie. And if we run the predict species function with this JSON data, then we get back the correct prediction here. So let's add this function to our FastAPI app using, again, a decorator. So this particular decorator will tell FastAPI app to call this function below Whenever the app receives a request to the predict path /predict using the HTTP post method, which will be used to post the data, FastAPI will automatically parse this JSON data in the request body to a Python dictionary named Penguin. So we've added that to our code here. We're also adding a more descriptive description parameter for our app. We put it all together, and now the code for our app looks like this. We'll run this cell, and we will try some examples. Click on the public URL. We will click on predict, then the try it out button. This request body field becomes editable. So we'll copy and paste Gary Gentoo's measurements into this field. A bill length of 45 millimeters and a bill depth of 15 millimeters. And click the execute button, then scroll down to server response. You should see the species Gentoo correctly classified. We'll try another example here. Copy paste Amy Adeli's measurements into the request body text field. And click the execute button. Scrolling down, you should see in the response body the species Adeli correctly classified. But what happens here if we change our request body to something unexpected? For example, what if our input does not have exactly two keys, bill length millimeter and bill depth millimeter, in that order? Well, let's try leaving one off. I click execute, and I see here an internal server error with no helpful warning or error message. Worse, the app could seem to work and return a response. If I put in numbers, two numbers, I'm going to get back a response, but yet these inputs are flawed and the output therefore is flawed too. Garbage in, garbage out. So we want to add data validation next. To stop this cell from running, we'll move on to part 3. So this is our type annotation for the predict species function so far. The function takes an argument named Penguin, and this argument can be any Python dictionary. We're going to get more particular here. We'll change this so the function expects an argument of type Penguin, which will be a class that we define. A special type of Python class, a data class, with type annotation to define what attributes we expect our input, a penguin, to have, and what types we expect for each of those attributes. And we'll use Pydantic, which is a data validation library that's tightly integrated with FastAPI. Now, I know these sentences may sound dense and complex, but as you see here, it's just a few lines of code. So here is our Penguin class. We could instantiate a Penguin object like this, passing in the parameters for bill length and bill depth, or like this, getting the exact same result, unpacking our dictionary here into the parameters for the class's constructor. Now let's see what happens with some of our scenarios of bad or invalid data. For example, some missing input. If I execute this cell, I get a validation error. There's a helpful descriptive error message here. We have bill length millimeter, but bill depth millimeter is also a field required. We're missing that field. This is exactly what we want in this situation. We don't want a generic server error, and we certainly don't want it to just seem to work. Instead, we want intentionally to have a validation error here. Next, we'll try a misnamed input. In this case, build depth instead of build depth millimeter, again, we get this validation error because we're expecting a field named exactly build depth millimeter. Let's now try an input with the wrong type. For example, we've got build length millimeter and build depth millimeter, but build depth millimeter is a string, hello penguins. It's the wrong type, string instead of a number. We get a validation error because the value here is not a valid float. And we said in our penguin class that build depth millimeter needs to be a float. Now we'll try a different string here. We'll do build depth millimeter as a string containing the number 15. This does not give us an error here. This works because this string can be converted to a float, and that's exactly what happened here. The string 15 was converted to the float 15.0. Also, here the integer 45 was converted to the float 45.0. A couple more scenarios. If we add an extra input, look, it will just be ignored. It will be dropped. If we flip the order of inputs, the build depth before the build length, doesn't matter. They'll be flipped back. All right, one more scenario that we need to validate. What about these penguin measurements if they're impossibly large or small? Well, we can use constrained floats to catch this. We'll import constrained float from Pydantic. See a variety of options here, including we can set constraints that each input must be greater than some minimum and less than some maximum. So what would be reasonable constraints? Well, let's look at the minimum and maximum measurements from our training data. And we see here the shortest and longest build lengths that we've observed and the shallowest and deepest build depths that we observed in the training data. We'll use these here as some reasonable, plausible constraints. So you say now that build length millimeter isn't just any float, which could range from -infinity to +infinity, but instead it's a constrained float that must be greater than 32 millimeters and less than 60 millimeters. Similarly, build depth must be greater than 13 millimeters and less than 22 millimeters. And now, when our inputs are too large or small, we will get an appropriate validation error with descriptive messages. Like in this case, an impossibly huge penguin, we get the validation error. Say that we need to make sure the length and depth are less than the maximum here. What if we were to set build depth and length of 0? A 0 penguin. What does that mean? A penguin without a bill? A penguin that does not exist? Regardless here, we get a validation error intentionally. Say that the length and depth must be greater than the minimum. We get the exact same error if we were to do negative measurements here for the depth and the length, which would not make sense here. Great. We're almost done with this class that we'll use to parse and validate our penguin measurements. But one more thing here. We're going to add a helpful method to our class, this toDataFrame method. It's going to use some of the code that we are prototyping before in our notebook to convert a dictionary to a pandas data frame with one row. Putting it all together here, now we could take data that looks like JSON or is a Python dictionary and validate it and convert it to a pandas data frame with one line of code like this. There we go. Let's put this all together in our FastAPI code. So recapping, we are adding this penguin class here. We're changing the type annotation here for the predict species functions argument. So instead of any dictionary, the type expected is now penguin. And when a post request is made to the predict path, then FastAPI will automatically validate and parse the request body's JSON into a penguin object for us. And then here we will use the Penguin objects to data frame method to convert that input data into a format that will work for our classifier's predict method. So we will run this code cell. Now we will test the app. We click on predict. We see now our doc string automatically pull into this documentation. Click try it out. And now if bill length and depth are 0, we execute. We get a validation error here with helpful error messages. If we use valid inputs, it still works as before. All right, we've got an app that is working. It's running from a notebook. So let's stop this cell. And our last part here is to get ready for deployment. So one thing you may want to do is to save your model so you could use it without retraining it. We sometimes call this pickling. And you can see scikit-learn's docs on model persistence. Recommend using a library called joblib to save your model as a file. And now if we were to delete this classifier from our Python notebook's temporary memory, well, we could reload this classifier from our file. And look here, it's back, it's ready for use. We've got our classifier again. Now, if you were training your model in a cloud notebook like this, and you want to say, well, how do I get this file off of Binder servers onto my own computer? Well, you can use code like this to get a link to download this file to your local computer. Putting it all together, our final code cell here has 3 changes from our previous iteration. So we're going to load the model with joblib, like this, importing the load function from joblib, and then loading our classifier from the file. We are also adding some image HTML tags in the app's description here. Notice that these descriptions and doc strings can use HTML, they can use Markdown. And finally, we will configure CORS, an acronym for Cross-Origin Resource Sharing, so that our API could be called by apps on different domains. And that code is right here. Running this app in our notebook, we can click this ngrok link and we see the new images. You've successfully prototyped a complete working web app running from a notebook. The app is only available while a cell in your notebook is running. So what if you want to deploy a bit more permanently? If you want to take this last step and go beyond the notebook, see the README in this repo for step-by-step instructions how to deploy to Heroku, a popular cloud platform. The code is in the app subdirectory in a file named main.py. And this will look very familiar because it's the code that we just wrote together in our notebook. This is what will be deployed on Heroku. Let's demonstrate. First, log into Heroku. Create a new Heroku app with a randomly generated name. Push our local Git repository to Heroku. Our requirements will be installed. After a few minutes, our app has been deployed to Heroku. We can use the command Heroku open or simply copy and paste this URL here into our browser. And now we see our app. It is no longer dependent on a certain cell in a Jupyter notebook running. This is now deployed permanently on the internet, for us to use this user interface or to write other applications that call this application programming interface. Congratulations, you've prototyped an API in Jupyter and deployed it to the cloud. How will you apply these skills to your own projects? Best wishes to you in whatever you choose to build next.